compact conductor is a type of electrical conductor designed to minimize its size and maximize its current carrying capacity. It consists of multiple strands of conductor material twisted together in a specific pattern, forming a cylindrical shape. Compact conductors possess several key properties. Firstly, they have a smaller diameter compared to conventional round conductors. Secondly, they exhibit reduced surface area, which decreases corona loss and radio interference. Thirdly, they demonstrate improved current carrying capacity due to better surface contact between strands. Fourthly, they offer higher flexibility and resistance to vibration. Finally, they are suitable for use in overhead lines, underground cables, and busbars. Compact conductors are widely used in various electrical applications. 1. They are used in overhead transmission and distribution lines to increase power transmission capacity without requiring new towers or right-of-ways. 2. They are used in underground cables to minimize trenching costs and reduce voltage drop in urban areas. 3. They are used in substations and electrical switchgears busbars to handle high currents in a compact space. 4. They are used in industrial and commercial installations for power distribution and equipment interconnection. Compact conductors are typically preferred in situations where firstly space is constrained or aesthetically important. Secondly, current carrying capacity needs to be maximized. Thirdly, corona loss and radio interference must be minimized. Fourthly, flexibility and vibration resistance are required. Understanding these properties and applications is crucial for electrical engineers and technicians when selecting the appropriate conductor for a specific project. The reduced size and enhanced performance of compact conductors make them a valuable solution for modern electrical systems. When working with electrical systems, safety should always be prioritized. Ensure that all installations and maintenance are carried out by qualified personnel following established safety procedures. Proper grounding and insulation are essential to prevent electrical shock and equipment damage. Always de-energize circuits before performing any work, and use appropriate personal protective equipment, or PPE, such as gloves and eye protection. When dealing with high-voltage applications, maintain safe clearance distances and use specialized tools and equipment designed for the voltage level. Regularly inspect electrical systems for signs of wear and tear, and promptly address any issues to prevent hazards. By adhering to these safety precautions, you can ensure a safe working environment and prevent accidents. The construction of compact conductors involves several steps to ensure optimal performance and reliability. Firstly, the individual strands of conductor material, typically aluminum or copper, are carefully selected for their conductivity and mechanical properties. Secondly, these strands are then precisely twisted together in a specific pattern using specialized machinery. The twisting pattern is designed to maximize the contact area between strands, reducing electrical resistance and improving current carrying capacity. Thirdly, the compact conductor may undergo a compaction process, further reducing its diameter and increasing its density. This process involves applying pressure to the conductor to eliminate air gaps and ensure a tight fit between the strands. Fourthly, the compacted conductor is then tested to verify its electrical and mechanical properties. These tests include measurements of resistance, tensile strength, and elongation to ensure that the conductor meets the required specifications. Finally, the compact conductor is typically coated with a protective layer to prevent corrosion and protect it from environmental factors. This coating may be applied using various methods, such as extrusion or painting. The specific construction techniques and materials used may vary depending on the application and the desired performance characteristics of the compact conductor. However, the overall goal is to create a conductor that is smaller, lighter, and more efficient than conventional wound conductors. The improved current carrying capacity of compact conductors is a result of several factors. Firstly, the increased surface contact between strands reduces electrical resistance, allowing for more efficient current flow. Secondly, the reduced diameter of compact conductors allows for better heat dissipation, preventing overheating and increasing the allowable current. Thirdly, the compact design minimizes air gaps within the conductor, reducing the risk of corona discharge and improving insulation performance. The specific current carrying capacity of a compact conductor depends on several factors, including the conductor material, size, and operating temperature. Therefore, it is essential to consult relevant standards and specifications to determine the appropriate conductor for a given application. In addition to their improved current carrying capacity, compact conductors also offer several other advantages. Firstly, their smaller size and lighter weight make them easier to install and handle, reducing labor costs and installation time. Secondly, their reduced surface area minimizes wind and ice loading, reducing the stress on supporting structures. Thirdly, their higher flexibility and resistance to vibration make them more durable and reliable in harsh environments. The use of compact conductors in overhead transmission lines has several significant benefits. Firstly, it allows for increased power transmission capacity without requiring new towers or right-of-ways. This can save significant costs and reduce environmental impact. Secondly, it reduces coronal loss and radio interference, improving the efficiency and reliability of the transmission system. Thirdly, it minimizes the visual impact of the transmission lines, improving aesthetics and public acceptance. The design and installation of overhead transmission lines using compact conductors require careful consideration of several factors. Firstly, the conductor size and type must be selected based on the required current carrying capacity, voltage level, and environmental conditions. Secondly, the tower spacing and conductor size must be optimized to minimize stress on the conductors and supporting structures. Thirdly, the installation must be performed by qualified personnel using specialized equipment and techniques. The use of compact conductors in underground cables offers several advantages in urban areas. Firstly, it minimizes trenching costs and reduces disruption to traffic and businesses. Secondly, it reduces voltage drop, improving the quality of power delivered to consumers. Thirdly, it allows for higher power density in underground conduits, maximizing the use of available space. The design and installation of underground cables using compact conductors require careful consideration of several factors. Firstly, the cable size and type must be selected based on the required current carrying capacity, voltage level, and soil conditions. Secondly, the cable must be properly insulated and protected from moisture and mechanical damage. Thirdly, the installation must be performed by qualified personnel using specialized equipment and techniques. The use of compact conductors in substations and electrical switchgear offers several benefits. Firstly, it allows for higher current handling capacity in a compact space, minimizing the footprint of the substation. Secondly, it reduces the risk of short circuits and ground faults, improving the safety and reliability of the substation. Thirdly, it simplifies maintenance and reduces downtime. The design and installation of bus bars using compact conductors require careful consideration of several factors. Firstly, the conductor size and type must be selected based on the required current carrying capacity, voltage level, and operating temperature. Secondly, the bus bars must be properly supported and insulated to prevent shorts and ground faults. Thirdly, the installation must be performed by qualified personnel using specialized equipment and techniques. In industrial and commercial installations, compact conductors are widely used for power distribution and equipment interconnection. They offer several advantages in these applications. Firstly, they reduce the size and weight of electrical panels and enclosures. Secondly, they simplify wiring and reduce installation time. Thirdly, they improve the efficiency and reliability of the electrical system. The selection and installation of compact conductors in industrial and commercial installations require careful consideration of several factors. Firstly, the conductor size and type must be selected based on the required current carrying capacity, voltage level, and environmental conditions. Secondly, the conductors must be properly protected from mechanical damage, moisture, and chemicals. Thirdly, the installation must be performed by qualified personnel following all applicable codes and standards, such as the National Electrical Code, or NEC. The NEC provides specific requirements for the selection, installation, and protection of electrical conductors. These requirements are designed to ensure the safety and reliability of electrical systems. When working with compact conductors, it is essential to consult the NEC to ensure compliance with all applicable regulations. For example, NEC Table 310.15b16 provides ampacity ratings for various conductor types and sizes. This table is used to determine the allowable current carrying capacity of a conductor based on its insulation type and ambient temperature. The NEC also provides requirements for conductor derating, which is the reduction of ampacity to account for factors such as ambient temperature, conductor bundling, and conduit fill. Proper derating is essential to prevent overheating and ensure the safe operation of electrical systems. In addition to the NEC, other standards and specifications may apply to compact conductors. These standards may cover topics such as conductor construction, testing, and performance. It is essential to consult these standards to ensure that the compact conductors used in a particular application meet the required specifications. When selecting a compact conductor, it is important to consider several factors. Firstly, the conductor material should be chosen based on the required conductivity, strength, and corrosion resistance. Aluminum is a common choice for overhead transmission lines due to its lightweight and high conductivity. Copper is often preferred for underground cables and building wiring due to its higher conductivity and flexibility. Secondly, the conductor size should be selected based on the required current carrying capacity, voltage drop, and mechanical strength. Larger conductors can carry more current and have lower voltage drop, but they are also more expensive and difficult to install. Thirdly, the conductor insulation should be selected based on the voltage level, operating temperature, and environmental conditions. Different insulation types have different voltage ratings and temperature ranges. Fourthly, the conductor construction should be selected based on the application requirements. Compact conductors are available in various constructions, including stranded, compressed, and compact round. The choice of construction depends on factors such as flexibility, vibration resistance, and corona performance. Fifthly, the conductor coating should be selected based on the environmental conditions. Conductors may be coated with various materials to protect them from corrosion, abrasion, and ultraviolet radiation. Proper installation is essential to ensure the performance and reliability of compact conductors. Firstly, conductors should be handled carefully to avoid damage to the insulation or conductor strands. Secondly, conductors should be installed according to the manufacturer's instructions and all applicable codes and standards. Thirdly, conductors should be properly supported and secured to prevent excessive stress and vibration. Fourthly, conductors should be terminated using appropriate connectors and tools. Improper terminations can cause overheating and premature failure. Fifthly, conductors should be tested after installation to verify their integrity and performance. These tests may include insulation resistance testing, continuity testing, and voltage drop testing. Regular maintenance is essential to ensure the long-term performance of compact conductors. Firstly, conductors should be visually inspected for signs of damage, corrosion, or overheating. Secondly, connections should be checked for tightness and corrosion. Thirdly, insulation should be inspected for cracks, cuts, or other damage. Fourthly, conductors should be cleaned periodically to remove dirt, dust, and other contaminants. Fifthly, conductors should be retested periodically to verify their integrity and performance. When replacing compact conductors, it is important to select a replacement conductor that meets the original specifications. The replacement conductor should have the same material, size, insulation, and construction as the original conductor. It should also be installed according to the manufacturer's instructions and all applicable codes and standards. In conclusion, compact conductors are a valuable solution for modern electrical systems. They offer several advantages over conventional round conductors, including smaller size, improved current carrying capacity, and reduced corona loss. By understanding the properties, applications, and installation requirements of compact conductors, electrical engineers and technicians can effectively utilize them to design and maintain efficient and reliable electrical systems. Remember to prioritize safety and always follow established safety procedures when working with electrical systems. In addition to the points already covered, it is also beneficial to consider the environmental impact of conductor selection. Choosing materials and designs that promote energy efficiency and reduce waste can contribute to a more sustainable electrical infrastructure. For instance, using recycled materials in conductor manufacturing or implementing smart grid technologies to optimize energy distribution can minimize the overall environmental footprint. Moreover, proper disposal and recycling of old conductors are crucial to prevent environmental contamination and recover valuable resources. Partnering with reputable recycling facilities ensures that these materials are processed responsibly and reused in new applications. Considering the entire life cycle of electrical conductors from manufacturing to disposal can help create a more sustainable and environmentally friendly power system. Finally, staying updated with the latest advancements in conductor technology is essential for electrical professionals. Continuous learning and professional development allow engineers and technicians to leverage new materials, designs, and installation techniques to improve the performance and efficiency of electrical systems. This may involve attending industry conferences, participating in training programs, or pursuing advanced degrees in electrical engineering. By embracing innovation and staying informed about emerging technologies, electrical professionals can contribute to the development of a more reliable, efficient, and sustainable electrical infrastructure. It is also important to understand the impact of harmonic currents on compact conductors. Harmonic currents are non-sinusoidal currents that can cause overheating and premature failure of electrical equipment, including conductors. Compact conductors are particularly susceptible to harmonic currents due to their smaller size and higher current density. To mitigate the effects of harmonic currents, it is important to use appropriate harmonic mitigation techniques, such as harmonic filters and reactors. These devices can reduce the amplitude of harmonic currents and prevent them from causing damage to electrical equipment. Another important consideration is the impact of electromagnetic interference, or EMI, on compact conductors. EMI is unwanted electromagnetic energy that can interfere with the operation of electronic equipment. Compact conductors can act as antennas, radiating and receiving EMI. To minimize EMI, it is important to use shielded conductors and grounding techniques. Shielded conductors have a layer of conductive material that surrounds the conductor and blocks EMI. Grounding techniques provide a low impedance path for EMI to flow to ground, preventing it from interfering with electronic equipment. When working with compact conductors in hazardous locations, it is important to follow all applicable codes and standards, such as the National Electrical Code, or NEC, Article 500 through 516. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Compact conductors used in hazardous locations must be specially designed and installed to prevent ignition of these materials. This may involve using explosion-proof enclosures, intrinsically safe circuits, and other safety measures. In addition to the technical aspects of compact conductors, it is also important to consider the economic aspects. The cost of compact conductors can vary depending on the material, size, and construction. It is important to compare the cost of compact conductors to the cost of conventional conductors and other alternatives to determine the most cost-effective solution for a given application. The economic analysis should consider the total cost of ownership, including the cost of materials, installation, maintenance, and energy losses. In some cases, the higher initial cost of compact conductors may be offset by lower operating costs and longer service life. Ultimately, the decision to use compact conductors should be based on a careful evaluation of all the relevant factors, including technical performance, safety, environmental impact, and economic considerations. By considering all of these factors, electrical engineers and technicians can make informed decisions that will lead to the design and implementation of efficient, reliable, and sustainable electrical systems.